And as you're familiar with our friends, Lucia and Manuel, we will be learning along them about the GC columns, about their properties, how they work, and what different properties, how they affect our results, and how to keep our columns in the best condition for longer. So as always, I would like to remind you that Trajan is able to provide you with all the GC consumables required for running your applications for your GC. And within those products, they are syringes, septa, ferrules, columns, injection port liners, gas filters, and various types of unions and splitters. But today, as I've mentioned, we will focus just on columns, as this product is the most complex and it's doing the main work in chromatography, so separation. A little reminder, what is chromatography? So this is a process of separation of components within a mixture, and this is done by our mobile phase, which is gaseous in gas chromatography, and stationary phase, which is inside our columns. The different components of the mixture travel with different speed within our column through our stationary phase. And this is allowing us to separate them one from another. And another nature of stationary phase is determining which substances are traveling quicker, which slower, and how they are getting separated. And the difference in the travel times within the column are called retention time. So how long our components are staying or how fast are they traveling through our column. So in gas chromatography, our components are getting vaporized in injection port, regardless of their initial state. And we've learned about vaporization during the last session, during the session about injection port, and then with a gas, they are carried through our column, which is covered with stationary phase. And the gases used in gas chromatography are inert. Usually they are nitrogen, helium, or hydrogen. And larger molecules within our samples, within our mixtures, are taking longer to pass through the column to reach the detector on the another end of our column. So what is the GC column? So in a short words, it's a very, very long tube, glass tube, fused silica, which is covered from the outside with polyamide coating. And this coating is providing the flexibility for our columns. Otherwise, without this coating, our columns will be constantly breaking because they are made of glass. And the inner layer is called stationary phase. And stationary phase is a film of high molecular weight polymer, which is coating the inner wall of fused silica. And this is where the separation occurs in the chromatography. So here we've got a diagram how the GC column works. So after the sample is vaporized, it's taken from the injection port onto the column. And at the top, you've got image where our sample is our mixture is in one place, and then with the gas flow, our components are getting separated to each of them, as each component has different properties, different weight, so will travel through the column in different speed. And at the end of our column, we've got detector, which is allowing us to visually present the results of the separation, and we are getting chromatograms with the peaks on them. So here are examples of how our peaks are looking like, what chromatogram is looking like, just the part of the chromatogram. So this is an output of our analysis of the chromatography run. So important characteristics of chromatogram is baseline. So it should be a flat line, and the peaks should be baseline resolved. So as you can see at the bottom, after one peak is finishing off, our signal should go to the bottom, to our baseline, and then another should appear. As you can see here, two above examples, we've got two peaks present, but they are not fully resolved. We don't have a baseline resolution, and in this case, we are calling the peaks, they are just partially resolved. Another characteristic in reading chromatogram is peak shape. As you've probably seen on your chromatograms, the peak shapes can look a little bit different for different compounds, for different types of analysis. Another characteristic is peak height, so how strong our signal is on our detector, and we are always able to observe the bleed in our chromatograms as well. So I will talk now a little bit about the column parameters, what they are and how they affect our chromatography, our results. So the columns are typically with internal diameter of 0.1 to 0.53 millimeters. The length of the column is between 110 to 120 meters. And another parameter to consider is film thickness. So how much of stationary phase we've got in our column, and the values for the film thickness can be anywhere between 0.1 to 5 microliters. And as I've mentioned earlier, the polyamide coating is increasing the flexibility of the glass, and it is allowing the coiling of the column, so we don't have like 120 meter long instruments, just the column is coiled inside the GC oven. So this is how our column is built, what parameters they've got, and I will go through each of them, how they can impact our chromatography and what parameters are typical for certain applications. So column ID is measured from, as you can see here on the diagram, inner diameter is the diameter of the fused silica inside, not including our stationary phase. So this parameter is important for maintaining the gas flow and pressure within our application. And here are some examples of different internal diameters columns and for which applications they are suitable. So the small diameter internal diameter columns are ideal for fast GC, for FID and ECD detectors. The columns with 0.22, 0.25 millimeter ID are ideal for mass spectrometry and high-resolution applications. 0.32 ID columns, they provide good resolution for most of applications. They are suitable for a wide range of applications, and they are compatible nearly with all the detector systems which can be connected to our GC. And the large ID columns, so 0.53, they are providing large sample capacities and ruggedness, so they are more robust than others. And here we've got an example of hydrocarbon analysis done on the normal column, let's say, so the column with 0.25 millimeter ID, and the fast GC, so with smaller diameter column, and you can see here the difference in the chromatogram. You can see that the separation is still good. We've got good resolution, but the analysis time is much shorter. So what does it mean for our analysis? That let me go back to column internal diameter. So the smaller ID of the column, the shorter analysis time would be. And this is the main rule to remember when we are looking to choose the columns and we are considering the column internal diameter. Next factor, next characteristic of the column is column length. And here we've got example of 3 chromatograms, the same application, the same type of the phase, the same film thickness, just the column length is different. And you can see at the top, we've got partially resolved peaks. We don't have a flat baseline between them. And this is the 15-meter column. The middle one is the same analysis done on the 30-meter column. As you can see, the resolution has increased, so the peaks are more further apart. And the last column is 60-meter column. The peaks are even further from each other with the better resolution. So increasing the column length will increase our analysis time. As you can see here, we've got 20-minute time span for all the chromatograms, and the shortest column, the peaks are on a shorter part of the chromatogram, are eluding at 3.7 minutes, in the 30-meter column 7.5 minutes, and in the 60-meter column our analysis is taking even longer, so 15 minutes. But the column length will allow us to have more stationary phase in them. So if we require increased capacity, it is a good solution to choose the longer columns. The longer columns will also provide us increased theoretical plates. So efficiency of the column will be higher. However, as I've mentioned, the longer the column will be, the longer analysis time will be, so because of the increased retention of our components within the column. Also, the longer the column, the higher the bleed will be comparing to the shorter columns. The next parameter of the column is film thickness. So how much of stationary phase we've got in our column. And here we've got 3 chromatograms again. The top one has the least the smallest film thickness, 0.25 micrometers. The middle one, 0.5 micrometers, and the bottom one, 1 micrometer. And as you can see again, the larger, the higher the film thickness, the longer analysis time is, as well as the better resolution it is for our peaks. So the peaks are more further apart with the higher film thickness. So the film thickness increased will increase our retention of our compounds in the stationary phase. So it will increase resolution for, especially for early eluting analytes. So the analytes which we are seeing at the beginning of our chromatogram. The more of the stationary phase, so the higher the film thickness, the more capacity the column has. And maybe it's not always considered, but the higher the film thickness, the less active the column will be. So the coating of the stationary phase of the column is providing us the better efficiency. But again, there is also a drawback in having the thick film in our columns. The thicker film, the more bleed we will see in our results. So talking about the stationary phase and its thickness, so there is a lot of different phases in our GC range, and we tend to sort them out by the polarity. So starting from non-polar columns as BP1, and the 5% phenyl columns as BP5, BP5 MS. Then we've got medium polarity columns as BPX35, BP10. Columns for volatile compounds are falling within the medium polarity range, and the more polar columns as a wax columns or FAME as BPX70, BPX90. And depending on our application, we will choose different polarity of the columns. We need to choose the column which is the least, the most suitable for our compound. So we need to also consider the polarity of our analytes, our components which we would like to analyze. And here is an example how different columns, so columns with different polarities, are showing us results for the same compounds for the same analysis. So the bottom chromatogram, the blue one, is done on the BPX5 column. And you can see that the peaks 6 and 7 are merged, so are not resolved. They are co-eluting. But on the column BP5 MS, even though there is very little difference in the phase composition, the peaks are resolved. Going further into more polar column, HT8 column, you can see that the peaks 6 and 7 even are swapping places. So elution order is different. Peak 7 is eluting earlier than the peak 6. And on the non-polar column, so BP1 column, we do have also those peaks resolved, but the 6 is eluting first, then the 7th. So as you can see, even small differences in the composition of our stationary phase may affect our results, what we see on our chromatograms. And another example is analysis of solvents, so benzene, toluene, ethylbenzene, and xylenes. And the top chromatogram is done on BP1 column, so non-polar column, and the peaks 4 and 5 are co-eluting. so we are not able to separate the para and monoxylenes. But when we move this analysis onto more polar column, so wax column, we can see that all xylenes are separated. So all isomers we are able to analyze all isomers of xylene. So this is why it's important to choose the right column for our analysis. And I believe this is the hardest task for anyone during the method development, to choose the right column for their application. And talking about applications, GC columns can be used in a wide range of different applications. And here I've put some examples. Which columns can be used in which industry? In forensics, we can use medium polarity column as BPX50. In the food industry, medium polarity column BPX35, as well as polar column BP20. In environmental analysis, so let's say pesticides, the BPX5 would work the best. And for volatile compounds, so solvents, BP624. In pharmaceuticals, BPX35. In water, again, BP624 will be suitable. Fragrance, wax column, so BP20. In petrochemicals, we can use a wider range of the columns, so starting from the most polar column available, like BPX90, to non-polar column, BP1 for hydrocarbon analysis, and HT5 for like a standard general purpose column. And as I mentioned earlier, pesticides, BPX5. So we do have also the selection guides for our columns. So for they can be found on our website, and for different types of compounds, we will have the recommendation of the stationary phase of the column. As well, we have also the table where we recommend the columns for specific applications required by the accreditation bodies, and accredited methods are also listed there with column recommendations. So we've got a column, we know what it is, what it does, and now how to install the column in our GC, how to do it correctly. So here's a diagram of the injection port. I hope you're familiar with the injection port from our last session. So the capillary column is going from the bottom into our injection port, and it's held there by the ferrule and the column nut. Here is the distance A. It is very important to measure accurately the distance from the ferrule to the tip of the column to position our column correctly in our GC instrument. And different GC manufacturers will provide you their recommendation, so we should always stick to the recommendation. The column should be in the right position all the time for our analysis to work properly. So how to install the column? First, we need to cool down our GC, as most of the time it's hot. Then we need to cut the column. And the cutting of the column should be done after the ferrule is installed. And the cut should be square, flat, without any uneven surfaces. Then we are able to connect the column to the inlet. We should establish the flow and purge our column with the oxygen-free gas. It can be done by our carrier gas. After the column is flushed with the gas, it should be connected to detector. Then after connection to detector, we can do the leak check if our system is sealed, if we don't have any leaks. Then we can set up our flow, so linear velocity of our gas in our application, and then we should heat the injector and detector, and we can proceed to conditioning of our column. And during the installation, I've mentioned that the column should be positioned in the right distance in our injection port. And here is example how the positioning of the column in the injection port can affect our chromatogram, our analysis. So on the top, we've got column, which is positioned correctly in our injection port. Below chromatogram is where the column was positioned too low in our injection port. So you can see our peaks are tailing. We can see the raised baseline towards the end of the chromatogram. So this is the sign that we didn't position the column correctly in our injection port. Another thing which can happen during the column installation is that we can the pieces of the graphite ferrules can enter our column and can be stuck in our column, and this is why we recommend cutting the column just a little bit to 2 centimeters after the ferrule installation, so we can avoid this problem. And here we've got examples of the chromatogram. At the top, we've got normal signal, normal response, so the peak heights are correct. When our sample was interacting with the graphite from our ferrule, which managed to get into our column, we can see the signal is much lower, the peaks are much slower comparing to the correct positioning, correct installation of the column. And column conditioning. So why do we need to condition the columns? The conditioning of the columns is removing contaminants from our column, is improving the peak shapes and extending the column lifetime. So it is important to condition the columns for our analysis to work properly as expected, and the conditioning should be done at 20 degrees above the highest method temperature you're doing, or up to the maximum specified operating temperature of the column provided by the manufacturer. So which one we should choose? We should choose the lower of the two. So when the column is exposed to higher temperatures, it will degrade faster. So the lower temperatures are the longer column could last. And we've heard something like column bleed here today. And here are examples of the profile, bleed profile for 100% methyl columns, so non-polar columns, even though they've got the same stationary phase. As you can see here, the bleed profiles are different and can be different. And we've got here as example BP1 column, Solgel 1 MS column, and column from our competitor, which is also non-polar column, 100% methyl column. And even though the phases of the columns are the same, the bonding of the phase to fused silica is done differently. So the sol gel 1ms is bonded to the fused silica using our sol gel matrix. And this is providing us the columns with lower bleed. And we will think, okay, all columns do bleed, but why it's important to have the low bleed? So here we've got example where we've got high bleed columns and low bleed columns. The low bleed columns are providing us much easier quantification and quantitation. The peaks are looking nicer, sharper. Our baseline is flat all along. When on the column with the high bleed, our baseline is raising when the temperature of our analysis is raising. So the bleed of the column can also increase with the time, and this is happening where our column is deteriorating, so it's becoming no longer suitable to our analysis. And here are examples of the things which can deteriorate our column. So dirty samples can deteriorate our column, and this is important. Possibly you remember from our last session why we should change the liners to clean ones, so we can extend our column lifetime. Very acidic and basic samples are having an effect of on our stationary phase of our column, are degrading the stationary phase. The poor gas management is also contributing to the column deterioration. So the gas filters, gas purifiers need to be changed also on a regular basis. Overheating our columns can also damage them. So we should always stick to maximum temperatures provided by the manufacturers on the column for each column. And for each column, the temperatures can be different. Also, incorrect storage of the column can contribute to deterioration. So how we can tell that our column is getting bad, getting damaged, deteriorated. So here are 8 points from which we can conclude that our column is deteriorating. So excessive baseline noise, retention time shift, change in the peak size, fronting peaks, tailing peaks, split peaks. We can lose our resolution, and we can observe the change in peak size. So excessive baseline noise. Here we've got example that our baseline should be flat. It should be just the straight line as long as possible. And the things which can cause column excessive baseline noise is the column contamination. To prevent the column contamination, or to aid when we do have contaminated column, we can do the bake out of the column and or implement backflash to avoid contamination. The solvent rinsing of the column can also causing the excessive baseline noise, and the solvent rinsing should be only done for bonded or cross-linked phases. And we should also check the inlet for contamination. And we can also observe the excessive baseline noise when our column is inserted too far into the detector. So as I mentioned earlier, the column should be positioned correctly in our injection port, but also how we insert our detector, the column to our detector is also playing a role here. So we should, if we are observing the excessive baseline noise, we should reinstall the column and check our GC manual for insertion distance. Retention time shift. So here we've got examples how the retention time can be shifting in our columns when something is not getting right. So the first peak is allotting at 2 minutes, but should be allotting at 2.75. And then every next peak is also shifting. So the retention time shift can be caused by change in column temperature. So we should check the column maximum temperature, and sometimes not all of the peaks will shift by the same amount of time, so they can be also co-alloting. So we will be losing our resolution. And the change in column dimensions can also will also be resulting in retention time shift. So we should remember which column dimension we've got for our analysis to remember to have those parameters the same. And we should measure also the flow of our gas, as the flow and pressure of our gases will be different in different column lengths and column IDs. The next issue which we can observe related to the GC column is the baseline instability, and how we can tell that this is the baseline instability but not column bleed. So as you could see on the previous slides, the bleed was increasing with the temperature and increasing toward the ends of the run. When our baseline is unstable, we will see the increases either at the end, in the middle, then drop down of the signal towards the end. So it can be very, very random, while the bleed is always increasing towards the end of the run in increased temperatures. And the baseline instability can be caused by column contamination or incompletely conditioned columns. So when we've got contaminated column, we can bake out the column, so trying to restore the functionality of our column or implement a backflush. And also when our column is not conditioned properly and completely, we should do the full procedure of the column conditioning. And this is the critical step for the trace level analysis. So the fourth issue attributed to our GC columns are fronting peaks. And here we've got example how our peak should be looking like. The shape should be symmetrical. And fronting is where we've got a tail at the front of the peak, but also fronting can be looking very similar to overload of the column. Overload of the column is when we do inject too much of our sample. So we should reduce the amount of our sample injected into our GC system. So either through lower injection volume or increasing the split ratio in our injection port, or diluting the sample. And this is the most common cause for fronting peaks and overload. Also, improper column installation can be causing the fronting. So when our column is not correctly positioned in the injection port. But this we should see during the first run after our column installation, and we can always compare what our results were in the past or previously on the same column or on the same column type. Another issue is tailing peaks. So again, we've had symmetrical shape of the peaks, and then we've got a tail on the right side of our peaks on the chromatogram. And the tailing peaks are caused by column contamination or column activity. When we've got contamination in our column, the best way is to trim our column. It depends how much of the contamination we've got, how the peaks are tailing, but we should remove like a fairly good chunk of our column, not just a few centimeters, up to even 30 centimeters will be good for getting our contamination out. We can also do the backflush of the column to avoid the contamination, and we can solvent rinse the column, but this can be only done for cross-linked phases and bonded phases, and we should check our inlet for contamination as well if we are observing the tailing peaks. The column activity is irreversible, so after cutting the column, if we are still seeing the tailing peaks, we should replace our column to the new one. There is unfortunately nothing we can do to restore our column, and this effect is mainly when we are analyzing active compounds. Another issue which can be seen on our chromatograms when we've got issues with our columns are the split peaks. And this is mainly caused by poor column installation. So the column should be reinstalled. And this is caused by improper insertion distance, either in injection port or the detector. So here you can see how many times I've mentioned that the correct positioning of the column is important, and how many problems can arise when it's not done properly. Change in the peak size. At the left, we've got example of our peaks, how they should be looking like. Going right, we've got a change of the size for all of the peaks, and sometimes we can observe the change of the peak size just for some peaks, not for all of the peaks all the time. This can be caused by column contamination and column activity. And as I mentioned earlier, if we do have contaminated column, we should trim the column from the injector end. So the front of the column we should cut out and implement a backflush. But when it's caused by column activity, unfortunately, we cannot do anything to restore our column. And the last issue attributed to GC columns is the loss of resolution. So when our separation of the peaks is not good, so when our peaks are merging and starting to collude, and this can be caused when we alter the column temperature, so the oven temperature of the analysis, different column dimension of the face. So when we're changing the columns to different phase to the one with different dimensions. And so we should verify which column should we use, and the loss of resolution can result in coillusion, so we should change the column temperature, and we should decrease the temperature of our analysis to check if the appearance of the peak is different. And this can be caused also by the column contamination. So again, trim the column, and backflash is the solution here, as well as the solvent rinse for bonded and cross-linked phases. So we talked about all the different problems which can be seen on our chromatograms, which are arising from the column and their degradation. So what can we do to avoid that or to fix that? So I will start from avoiding the problems, as this is the best route always to avoid the problems before they arise. So if we consider the use of the pre-column or guard column, we will be able to spot the issues earlier, so our column will not be damaged. We should check our flow rate and correct the flow rate of the gas in our analysis. We should avoid overheating of our columns if unnecessary, so using the lowest temperatures possible for our analysis. And we should support the column cage in the oven, so it always stay in the same place. There is no unnecessary movement. Also, using the good quality ferrules and changing them as needed will help us avoiding the column degradation. But if our column is degrading and we are seeing the signs, as explained earlier, we can trim the column, and we should trim the front end, so the injector end of the column, from at least 30 centimeters up to 1 meter. And we can also perform the column conditioning and bake out. And the bake out is similar to conditioning the column, but it is in its maximum continuous temperature for the longer period of time than just conditioning. We should remove the column and rinse with the inert solvent when our column is showing signs of degradation, but this can only be done with the columns with cross-linked phases, as otherwise we will wash out our stationary phase from the column. And if the column is not responding to any of those actions, it will be the time to change the column for the new. So here is example of the restoration of the column. So bake out procedure. So the first chromatogram, we've got reference run, how it should be looking like. The second chromatogram, you can see that the third peak is disappearing. So we've got only single peak, not a pair of peaks. And this column was conditioned at 300 degrees for 2 hours. And after the conditioning, so after bake out, we can see that the additional peak, the third peak, started appearing again. And our analysis time was getting shorter. So after further conditioning in a higher temperature, so 370 degrees for 6 hours, we can see that the peaks get back to our reference run. So, and the time of analysis has extended to the value where it should be. So this is, in a short example, how the bakeout procedure can be looking like. And in this example, the column BPX5 was used, so 5% phenyl columns. But please remember that the temperatures of the bake-out procedure will be different for different columns, and it should be done accordingly to maximum temperatures of the column. And then column storage. Most of the time our columns are working, performing analysis in our GC, but sometimes we are giving them a rest. So how we should store the column? In a short-term storage in the oven. So after our sequence, after is done, we should set up the program of the oven to the lower temperatures up to 100 degrees. The gas flow should be decreased to about 0.5 milliliter per minute. And we can also lower the detector temperature, and this will also extend the life of our column. But long-term storage, when we remove the column from our oven, if we want to use this column again, we should store the column in the original box. So this is the best way to protect our columns from scratching or breaking. We should write the history on the box, how our column was used for how long, or in logbook, if we do have a logbook for the columns. And we always should seal the column ends. And we should mark the inlet end as well as detector end, as if we would like to install the column again, we will know which end to connect to, either detector or injector. And for sealing the column ends, the easiest way is to use the GC septa. Just put the septa on the GC column. So going further, we've learned during the last session about the GC injection port consumables, and today about the columns. And the column is the most expensive consumable within our GC. So I would encourage everyone to check their small injection port consumables first, if they are in good condition, as they are much cheaper, and then we can avoid the column deterioration, so we can extend the column lifetime and we can spend less money on the most expensive bit. So if you need any further help troubleshooting the GC columns, please reach out. I hope I've made the topic of the GC columns easier for you, and you are more familiar with them, and you will be able to choose the correct columns for your applications. If not, please reach out to either your colleagues or to us. We are more than happy to help. And during the next session, we will be exploring another consumables related to GC, such as gas filters, ferrules, and various types of connectors. Thank you for your time today, and I hope to see you next time in a week.
Thank you, Paulina. See you next week. Pessoal, agradeço a todo mundo aí a participação. Nos vemos na próxima aula. E eu vou confirmar com vocês a questão da retransmissão da aula, tá bom? A gente vai se falando por e-mail. Qualquer dúvida, eu estou à disposição.